We're talking specifically about what happens to this bottle if we have 91 milliliters of water here. Now 91 milliliters would be closer about here. There's more than 91 milliliters here, but we heat the bottle so that water rises to the top of the tube. We then heat it some more, catch water as it flows into the upper reservoir. Then we're going to unscrew the cap or release a pressure valve, allowing the gas to expand very rapidly. And then we're going to cool the whole system down to the original state and add some water to get back up to the 91 milliliters so that we can do it all again. So that this cycle can repeat, and we can continue raising water to the height of the tube and collecting it, increasing the potential energy of whatever water reservoir we have down here. So we start with state 0. Now this is problem N1. In state 0 we have pressure P0, V0, T0. Now problem 1 didn't mention, but this is state 0, so I'm adding this. Okay, we have this state. We have initial pressure, volume, and temperature as are given, 500 milliliters, 91 milliliters of water. That's not important. Well, that's not a volume of air, so we're not really analyzing that 91 milliliters. It's just there to be raised, increasing the potential energy of the system. 100 kilopascals, 300 Kelvin. We want the temperature and pressure required to raise that water to a height of 1 meter. So we're raising water to a height of 1 meter in the tube. Okay, and we're going to call that a thin tube. It says in the problem, I mentioned it here, that the tube is thin, so there's a negligible amount of volume of water in that tube, meaning that the volume of the air in the container is going to remain pretty much constant. So, the question then becomes just what pressure do we need to support that 1 meter column? What extra pressure do we need? We can easily calculate that from Bernoulli's equation, and we get 10 kilopascals. Okay, so that the pressure in state 1, which we call P1, is 110 kilopascals. The volume is still 500 milliliters because there's negligible volume in the tube. There's no appreciable expansion of the air inside the bottle because there's no appreciable amount of water displaced from inside the bottle. And that's, of course, could be 500 milliliters can be expressed as 5/10,000ths of a cubic meter, or half of a liter. It's handy, as we mentioned, to know that if we multiply kilopascals by liters, we're multiplying thousands of pascals by thousands of cubic meters, and we end up with joules either way. We end up with units of newtons times meters either way. Don't use that shortcut unless you really understand why it applies. Go ahead and write this out as 110,000 pascals, or 110,000 newtons per square meter. Write this out as 0.0005 or 5 to the negative fourth cubic meters, and do the units carefully. In any case, the number of moles of air doesn't change. There's no way for air to get in or to escape the system, so that PV over T is constant, and it follows that P0 over V0, P0 V0 over T0 equals P1 V1 over T1. If we solve that for T1, we get this equation, which we ought to check by our intuition. To get a higher pressure, P1 being greater than P0, we need more temperature, so the P1 over P0 ratio makes sense. V1 over V0, if we expand the gas, if V1 was greater than V0, then that would also contribute to raising the temperature, and that ratio would be greater than 1. In this case, of course, V1 over V0 is 1 because there's no change in volume. P1 over P0 is 110 over 100. I'm really big on units, but when you have the same units in the numerator as in the denominator and you're very sure of that, you can just write the ratio of the numbers. The units are going to divide out as they have here. And anyhow, using this, we find that T1 is 330 Kelvin, and that the change in temperature is 30 Kelvin, as I believe Max mentioned. Okay?